All right, so thank you so much for that introduction. Exactly, I'll be telling you about how the minimum formula size problem is ETH hard. And I kind of, when I was designing this talk, I was thinking about what I wanted you guys to get away from the talk. And so I kind of designed this talk with kind of 5 questions in mind. And hopefully as we go through the talk, we'll get answers to these 5 questions. So I was asked to concentrate a lot on motivation and background. So the first part of the talk will be about that. And yeah. Okay, so we'll start with the most basic question. What is the minimum formula size problem? And yeah, feel free to interrupt me.
By the way, you're allowed to take your mask off if you
Oh, okay.
Still up you.
So yeah, and feel free to like interrupt me, shout me down, like if you have a question. Okay, great. So this talk is titled about the minimum formula size problem. But I'm going to start with the minimum formula size problem's more famous cousin, which is the minimum circuit size problem, and it's abbreviated MCSP. And at this point, you know, it's not clear why this is an interesting problem. I'm just going to tell you the definition, and yeah. So the minimum circuit size problem is going to take 2 inputs. The first, oh wait, actually maybe I should ask a poll. How many people here have heard of the definition of the minimum circuit size problem? I just wonder. Okay. So about like half-ish of the audience. Okay, good. So the minimum circuit size problem takes 2 inputs. The first is the truth table of a Boolean function. So you have some Boolean function, it takes n bits, it maps it to 1 bit, and then we can just write down all of the values that the function takes on all of its inputs. And I want to stress, this is like a really long string, right? Like, so if this Boolean function takes little n inputs, this is going to be a string of length 2 to the n. And our convention throughout the talk is that we're going to have this like capital N be 2 to the n. That's going to be the length of this input. And I'll remind you of this as we go on, so don't worry too much about it. So that's the first input, just some description of a Boolean function. And then the second thing is just going to be some size threshold. S is just some integer. And you can probably guess what's going to come next. We're going to say, does there exist a circuit with at most S gates computing F? And to be really precise here, I have to say precisely what model of computation I'm talking about here, what type of circuits I'm talking about. Yeah, for now, you can just think of it as some model of computation that uses gates and computes something. Maybe you can say the usual and or not gates, but we'll come back to that later. Are there any questions about the definition? Does it make sense? Okay, so just in case, I'll give it a quick example. So you could consider this function, the OR function, which just takes n bits and says, you know, is at least one of them 1. And then you could write down its truth table, which is just going to be 0 on the first bit and then like 1 everywhere else. This is a really long input. And you get some size threshold S. And, you know, if you consider your circuits to be like the usual type of circuits with OR and not gates and whatever, you can design a circuit for this OR function very simply by just taking OR of a bunch of stuff. And, you know, you output yes if this is greater than or equal to n minus 1, otherwise you output no. Okay. Hopefully it's clear. Yeah. All right, so that's the definition of the minimum circuit size problem. Let me tell you a little bit about it before I tell you why it might be interesting. Yeah. Seems like a simple question about circuits. What do we know about the complexity of this problem? We don't really know a lot. So we know that the problem is an NP. Hopefully this isn't too hard to see. So if you want to witness a yes instance to MCSP, what can you do? You can actually go in and hand over the circuit of size at most S. And the thing to note is that this truth table is very long. It's like 2 to the n. But that means if I was to hand you a circuit of size S, you can like evaluate that circuit on all of its inputs and check whether or not it computes this function. So hopefully it's not too hard to see that MCSP is an NP. What's not so easy to see is that this problem is probably not NP. It turns out that if all this good cryptographic stuff like one-way functions and pseudorandom generators exists, you can show that MCSP is not NP. So you have this kind of, you know, we know that it's an NP, it's probably not NP. The most natural question to ask is it NP complete? And this is kind of like the motivating question behind this talk. We have this problem, we know it's an NP, no, it's probably not NP, is it NP complete? And so that's what we know about the kind of the complexity about MCSP. And the title of this talk is about the minimum formula size problem. You can probably guess what that problem is going to be. it's going to be the same thing as this problem, except instead of we talking about circuits, we talk about formulas. And probably everyone here knows what a formula is, but if don't remember what a formula is, it's like a circuit, but every gate has at most one output. And I'm going to redefine it for you later, so in case you forgot. Great. So that's the definition of the minimum circuit size problem and the minimum formula size problem. There's one other thing that I kind of want to mention. We're not going to talk about it so much in this talk, but it turns out kind of like the most interesting version of this problem is the approximation version. So I hand you a truth table, and it's either guaranteed to have low complexity or guaranteed to have high complexity. And I ask you to distinguish between these two cases. And I kind of like to cheekily call this like the order versus chaos problem. Because you're either given this truth table, which has a lot of computational order, described by small circuits, or it's like kind of random looking. So I call it order versus chaos. We won't talk about it so much in this talk, but when we come back to open problems, I'll mention it again. Okay, any questions about the definitions? Great. All right, so now coming back to this talk outline, we have this first question: what is the minimum formula size problem? And it's saying something like, compute the formula complexity of a function. So you're given some description of a truth table, and you want to ask, how hard is it to compute with it? And now I want to say a little bit about why you might care about this family of problems: MCSP, MFSP. MFSP stands for minimum formula size problem. And so I thought I'd bring up this quote, which is kind of bold, which says MCSP is more fundamental than SAT. And this is kind of a daring claim to make, because like if you have two problems and your audience pretty much everybody in your audience knows about one problem, and you have to explain the other problem, it's kind of is one really more fundamental than the other? And so like SAT's a problem that has been really powerful in theoretical computer science, like by understanding the satisfiability problem. We learned about NP completeness, we learned about PCPs, all this stuff. Like what daring researcher would like dare utter this blasphemy like this problem MCSP? Yeah. So my name is Rahul, but this isn't me, Rahul. This is Rahul Santanam. And at this point, so you can point your pitchforks at him if you don't like this statement. But at this point, you're probably wondering, like, why are all these Rahuls interested in MCSP? There's some cult. They think it's better than SAT, whatever. What's going on here? And so let me tell you a little bit about why I think this problem is interesting. And I think primarily it has to do with the connections the problem has. So it has these kind of like surprising connections to other areas of theoretical computer science. So it has connections to cryptography, it has connections to learning theory, connections to structural complexity, average case complexity, circuit complexity. And in this talk, because it's not my main focus, I'm not going to talk too much about all of these. But on this slide, I wanted to give you like a little taste of what some of these connections are and how they're related to MCSP. So it has these connections, of which I haven't told you what they are yet. But other thing I want to mention about this problem is somehow it seems interconnected to these other areas of theoretical computer science. It's also like a big mystery. Like unlike like most problems in theoretical computer science, we don't really understand anything at all about its complexity. For example, is it NP complete? As I mentioned earlier, we don't know. Is it hard to approximate? We don't know. Is it hard on average? We also don't know. Is there anything better than the brute force algorithm? We also don't know. We really know very little about this problem. What's interesting though, is that like each of these questions that we don't have answers about are related to important questions in these areas. So let me give you a few examples of those. So in particular, I'm going to give you some theorem statements, which are of the following form. If we learn that something is true about MCSP, then that will imply some solution to an important question in one of these areas. So for example, what if we knew that MCSP is NP complete? If we knew that MCSP is NP complete, then by its theorem of Murray and Williams, you'll get a breakthrough complexity separation. It doesn't really matter what this is. I mean, it says that X is not equal to ZPP, which is something we believe, but it's something we don't know how to show. Like we don't know how to show this kind of separation. And if you show MCSP is NP complete under like the standard types of reductions, it actually implies this kind of breakthrough complexity separation, which is kind of interesting. Like a basic question about MCSP seems related to something else. Another thing that's interesting is if you can show an approximation to MCSP's NP complete, by this, like, this is one of my favorite theorems, a theorem of Hirahara. It actually shows that computing NP on average is as hard as computing NP in the worst case. So one of the big criticisms of complexity theory is that, like, it only works on worst case inputs. Like, what if you care about an average case distribution? In that case, we don't really have a good theory for connecting at least NP in the worst case to NP on average. And it was kind of like this big open question whether or not you could hope to get something like a worst case to average case reduction for NP. And it turns out that if this approximation problem is NP complete, you actually get this, which is kind of interesting. It seems to like suggest that this problem has some properties that, like most other NP complete problems, we at least don't know how to use.
Just a question about this. By on average, do you mean there exists a distribution?
Actually, you can say fix it to be like the uniform distribution, and this notion of average is going to be like zero error. So you're allowed to output yes, no, or question mark, and you have to get it with, you can't output question mark on too many of the things. Did that make sense?
Yeah.
Okay. Yeah. And so essentially, what this result is doing is it's giving a worst case to average case reduction to this approximation problem. So if we can prove this approximation problem is NP complete, we get great question. Any other questions so far? Awesome, thank you very much. And so the last result I want to mention is also very cool. So if you can show that MCSP is hard on average for some specific version of MCSP, then there's this very cool result by Liu and Pass, which shows that's actually equivalent to the existence of one-way functions. And so this is like a strong connection to cryptography. I've already mentioned on a previous slide that there's like some relationships to one-way functions existing implying MCSP is hard. This result actually shows you can get the other direction. And so that result's very cool. And maybe if you squint at these last two results, you might be like, hey, what's going on here? We show if MCSP is hard on average, then one-way functions exist. And some approximation to MCSP has a worst case to average case reduction. And so, like, can you combine those two results and get something that shows if this problem is hard on average, then you get one-way functions, maybe they're equivalent. And so there's some technical details here. If you're interested, I can tell you about it. But yeah, right now, it seems fundamentally the problem is that, like, this worst case to average case reduction works with actually one-sided error in one direction. And this also works with one-sided error, but the one-sided errors are in the opposite direction. So you can't compose them with each other yet, but maybe you can. And that would be awesome.
Was that the end of this? I have a question.
Yeah.
So there's all these whole connections if it's NP complete, and obviously if it's in P, then the world collapses. What about the intermediate situation?
Yeah, that's a good question. Like, what happens if MCSP is NP intermediate? I think it.
So that means like it's hard but not NP complete.
Yeah, like so you could imagine. Usually we separate things into like P versus NP complete, but we actually also know that if P is not equal to NP, there are live problems that are called NP intermediate problems, which are neither in P nor NP complete. And so there's this possibility, and in fact, some people believe this, like, so my undergraduate advisor, Eric Allender, is I think a strong proponent of the idea that MCSP should actually be NP intermediate. Maybe it's not NP complete. It should be, I mean, I don't know if he still believes this. I haven't talked to him about it in a little bit, but at the time, I think he seemed to believe this. And if it's NP intermediate, I'm not sure, like, if we have, because then you could hope to do maybe some sort of win-win, like either crypto doesn't exist, or we get this like worst case to average case reduction, or it's NP intermediate, in which case maybe you get something. I'm not sure. Like we don't really have a result that says like if it's NP intermediate and something happens. I think if it's NP intermediate, that would kind of suggest there's maybe like some weird complexity class that we haven't considered that's somehow between P and NP that has this like worst case to average case reduction property and is somehow related to crypto. Like maybe this class would capture crypto or something. I don't know. But yeah, it's an interesting question.
Have you thought about the relationship to statistical zero knowledge?
Oh, that's a great question. Yeah, it turns out, and so this is work that I think was by Allender and Das. So you can show that SCK reduces to MCSP. It actually, also all of these results, you can kind of prove versions of them for the minimum formula size problem. We'll get weaker parameters or something. But this result, the SCK hardness result, is kind of interesting in that it doesn't seem to also work for the minimum formula size problem. But Yeah, it's a great question. What's the relationship between SEK and MCSP? So as far as we know, the best hardness result we know for MCSP is that it's hard for SEK. So, which is like, maybe people don't know what SEK is, sorry. So there's this class of languages for which you can get these like statistical zero knowledge proofs for. If you haven't heard of statistical zero knowledge proofs, it's just some crypto wizardry, which is really awesome. You should check out. But anyway, it's just some cryptographically important class. So it kind of makes sense. MCSP is in some sense hard for crypto because if one-way functions, if MCSP is in P, one-way functions don't exist. So maybe it makes sense that you can get hardness for SEK as well. Great question. Any other questions? So this is kind of going to be the end of my general background on MCSP slide. Now I'm going to talk more about this question, which is the focus of our work, which is MCSP hard? Okay. So now in my talk outline, so far we've answered the following questions. So what is the minimum formula size problem? Computing formula complexity. What makes it interesting? I think primarily what makes it interesting is that it's a very mysterious problem. We don't really understand it. And somehow basic questions about it seem connected to other areas. And so that makes it kind of interesting thing to study. Is it more fundamental than SAT? I don't know if that's true yet, but yeah. Okay. So now let me tell you a little bit about the history of this question that we're studying. And I told you it's like this question is MCSP hard? So this is kind of the motivation for this work. And I like to call this a question older than time and space, and you'll see why in a second. So this problem has a very interesting history in that it was first asked, at least in some form, in the 1950s. In the Soviet Union, cyberneticians, I'm not totally sure how to pronounce it, were reading Shannon's work or reading Turing's work, and they're very interested in problems that they said required parabora, which says brute force search. They want to find problems for which there's no better algorithm, than just iterating through all the possible solutions and seeing if it works. And for whatever reason, they thought MCSP was like an ideal candidate for this. So they had conjectured that this problem requires brute force search. And to me, this is really cool because this is even before the time hierarchy theorem was proved. So time hierarchy theorem, I think is 1965 by Hermanus and Stearns. And so the time complexity classes haven't even been invented yet. The space complexity classes haven't even been invented yet. I mean, I'm sure, yeah, maybe there are some work that I missed. So I like to call this a question older than time and space complexity classes. And so in the 1950s, this question was asked. And in 1959, someone claimed they had a proof. So this guy, Jablonski, he claimed he had a proof, essentially showing, I mean, at the time there wasn't this language, that MCSP is not in P, which would be kind of astounding because had he actually shown this, he would have resolved P versus NP before the question was even asked. Of course, he didn't quite show this. It's actually a kind of interesting anecdote about this guy. He came into some scientific political power, and he was very convinced he had proved this result. So he kind of almost killed off the area because he didn't prove the result, but he claimed he proved the result, and he was in political power, so nobody else could work on the problem to some extent. Right. So this was 1959. 1969, somebody else also claimed to prove this parabolic conjecture, and they ended up proving what turns out to be that P is not equal to NP relative to an oracle. Of course, NP hadn't even been defined yet, but they had phrased it in terms of oracle Turing machines and stuff like that. So it's kind of interesting, the history of this problem. It kind of led to some interesting stuff. And then now I also want to mention some kind of fun quotes about this problem. So in 1973, Leonid Levin proves his version of the Cook-Levin theorem. And there's this really interesting quote on his blog. I'm sorry, it's pretty small, but I want to fit it in. I'll read it out to you. So in this blog post, he's talking about when he was proving his his version of the Cook-Levin theorem. And he actually, when he proved it, he didn't think it was so interesting. He was like, I don't know about this. I don't even want to publish it. His advisor was like, no, you should publish it. And he actually had only proved this result in some sense because his roommate was like, oh, theory's not good. His roommate was a combinatorial optimization person. And his roommate was like, oh, what are you doing with all this theory? Maybe it's not so useful, whatever. And so Levin was like, no, you can connect these things. And he ended up proving some combinatorial optimization problems are NP complete. But he still didn't think it was so interesting. He said, I only thought extending the theory of NP completeness to some proper problems like graph isomorphism, circuit minimization, or factoring would be worth publishing. I tried for a long time. And if you're interested in this, I can give you the link to the blog post. It's very nice. And it's kind of funny because like the problems he was trying to show are NP complete, graph isomorphism we now know is in basically P. Circuit minimization is this big open question, and factoring we know is like almost definitely not NP complete. So thank God he ended up publishing it anyway. He might have been there for quite a long time. So in some sense, this question of whether MCSP is NP hard is like, it goes all the way back to Levin. And then finally, there's kind of a fun quote that Ryan has, and he has this fun quote where he's talking about, he just wants to see what this NP completeness proof might look like. And he's like, if it's NP complete, it would have to require techniques that are not like any polynomial time reduction that we have ever seen. So anyway, so that's some of the history of the problem. I don't know if anybody has any questions here. Or, yeah. Anyway, so this question is, is MCSP NP hard, or hard in some sense, and it has some fun history. Okay, so now let me tell you a little bit about why showing this problem is hard. And as I've mentioned on the previous slide, it's something that people have thought about for a while. Like, so why is it difficult? I mean, there's thousands of problems that we know how to show that are NP complete. Why is this specific problem so difficult for us to get our handle on? And kind of the intuition that I have, and I think other people have as well, is that if you look at the difficult no instances of MCSP, like if you were trying to design a reduction from SAT to MCSP, what do you want to do? You're going to map difficult no instances of SAT to difficult no instances of MCSP. The trouble is, if you look at the difficult no instances of MCSP, what are they corresponding to? They're corresponding to like functions and size thresholds that are kind of large. So they're like functions that require large circuits. And we don't really know how to come up with these. Like, this is like a big open question. Can we come up with functions that require large circuits or that are hard to compute? We don't really know how to do it. So it's kind of difficult to imagine what a reduction would look like. Like, if you don't even have like non-trivial no instance of a problem, how are you going to get a reduction? And in fact, you can formalize this into.
So can I push back on that? Because if we allow randomized reductions, then
yeah, great.
You come up with functions that require large circuits.
Great. Yeah, I'll come to that actually, but that's a great point. Yeah, and so you can kind of formalize this intuition and say deterministic polynomial time reduction requires a breakthrough. And so yeah, this is exactly your point. So if you're aiming to get a deterministic polynomial time reduction, there's some barrier to doing that. And so what does this mean? Does this mean we're not ready to tackle this problem? Like, maybe this is just a hard problem. Like, we need circuit lower bounds to tackle it. We should come back to it when we have those or something like that. I don't think so. And in particular, there's kind of two holes here, right? Like, what if we're talking about deterministic reductions? What if you're allowed randomness? Another thing that's going to be kind of the focus of this talk is going to be, well, what if we don't care about polynomial time reductions? What if you allow yourself sub-exponential time reductions? And then I'll kind of describe later, these barriers kind of go away. And so let me just pause here and talk about this like deterministic versus randomness thing, since you brought it up. So yeah, so the point here is, even though we don't know explicit functions that require large circuits, it's very easy to come up with, if you're allowed to use randomness, it's very easy to come up with functions that require large circuits. You just pick one at random, uniformly at random, and then it'll require large circuits. So if you're allowed to use a randomized reduction, it's not clear if there is a barrier to showing MCSP is hard. Because like maybe you can get these functions requiring large circuits using uniform randomness. And in fact, there have been some proof of concepts of this. So like I have some reductions that I'm not going to talk about here, which actually kind of fundamentally use randomness in order to get hardness for versions of MCSP, or like different versions of MCSP. And so yeah, it seems like randomness can be useful for getting a reduction. But what seems to be weird is like just uniform randomness doesn't seem to be, like it seems like you need to use randomness in combination with some other lower bound technique, because like, yeah, and there's a couple ways to formalize this. There are these things called like oracle independent reductions that Shuichi Hirahara has defined, but in some sense, like it seems like lower bounds that just come from counting arguments, if you don't use anything else, it seems like they're not strong enough to show that MCSP is NP hard. But this idea of using randomness, like we don't have like we haven't ruled out that itself would be enough to give an NP hardness reduction. My intuition is that you can use it to help you get where you want to go, but it's not gonna, you're gonna need to use a different lower, you're gonna need to use a new lower bound in combination with the randomness. And so, yes, does that answer your question? Okay, great. And so this other way to avoid this barrier, which is what's gonna be kind of the concentration of this talk, is going to be like sub-exponential time reductions. So, usually when you define NP completeness, you say you care about reductions that run in polynomial time. But like, if we just want to show that this problem is difficult, why not concentrate on sub-exponential time reductions? And so here's a conjecture. I don't know if people here are familiar with the exponential time hypothesis, but roughly what it is, just some strengthening of P versus NP. So P versus NP says that like SAT can't be solved in polynomial time. Exponential time hypothesis roughly says that you can't solve SAT in sub-exponential time. So it's just some strengthening of the problem. And so this is a conjecture that the exponential time hypothesis should imply that MCSP is not NP. And as a conjecture, let me just say this is a very weak conjecture. I mean, if crypto exists, then like this part is true. I've already seen. So like the conjecture itself isn't very strong. What I'm really conjecturing is that I don't think this requires like seriously new techniques. I think we're practically like, we just need like one new idea to do this. Like, I mean, this is a problem that's been thought about for a while, but I mean, if you really get down to brass tacks, if you wanted to show just this thing, I think you just need like one new idea. And I mean, I've been thinking about it for a while, I haven't succeeded, but in this talk, I'll say about how we can do this for formulas. So we prove this conjecture for formulas. Okay, are there any questions?
I'm not sure it was clear to people, maybe even me also, I'm not sure.
Yeah.
Why the top, why the fact that nothing, no instance, no instance with deterministic reduction.
Yeah, sure. So maybe I'll write something. So like, so what are the no instances of MCSP? So the no instances, are you able to see this by the way? Okay. They're kind of pairs of truth tables and size parameters such that, let's just say the complexity of T is greater than S. So if it's a no instance of MCSP, then T does not have a circuit of size S, so its complexity is greater than S. And the thing, if you want a difficult no instance of MCSP, then you need to make sure that the size parameter is not too small, because there's a brute force algorithm. That's going to run in time roughly, I guess, like n to the s. At least for formulas, will run in time like n to the s. So in particular, if you're gonna show hardness for this problem, you want to make sure you show hardness. If you use a size parameter that's too small, your reduction is actually going to give you an algorithm. Does that make sense? And so because of that, you're going to need to use size parameters that are large. And size parameters that are large means that like truth tables that have high circuit complexity or whatever complexity. And we don't really know how to come up with those deterministically. So you might think it's hard to get a reduction.
I mean, we do know hard functions that these are uncomputable.
Oh, okay. Yeah, that's true. I guess like you're saying like maybe we can use a problem that's like I guess like what is it like double X or something.
I don't know.
Yeah, I see. But I guess the problem is then if you define explicit function to be something where you can print the truth table in polynomial time, which you would need to get a reduction. Yeah. Does that answer your question?
Yeah. I kind of think I knew that.
Okay. All right. Yeah. Does that make sense to everyone or? Okay. And yeah, feel free to stop me. If there's something you don't understand. Right. So thanks for that. All right. And so my last background slide before I get into the results is kind of taking a step back. So far, what have I told you? Let me skip forward for a second. So far, what have I told you? I've told you what the problem is, told you why you might find it interesting, and I have told you why it's hard to prove hardness. But let me take a step back and be like, okay, why am I interested in this hardness question, and why is like proving hardness interesting? Because like maybe MCSP as a problem is interesting, it's like connected to these other things. But maybe this question of NP hardness isn't so interesting because we already know the problem is cryptographically hard. Why care so much about proving NP hardness? Why is NP hardness so interesting? And to me, there's kind of three reasons. So one reason I care about it is I think it like as a problem, it forces me to think about new circuit lower bound techniques. So in terms of circuit complexity, like circuit complexity is a tough area in that there's not a lot of good intermediate problems. Like there's problems we know how to do, there's problems that's been open for like 40 years or something. There's not a lot in between. So if you want to like make advances in the fields, what you'd like to have is you'd like to have some good intermediate problems, which kind of like point you in the right direction. And in circuit complexity, like these are kind of hard to find. And proving hardness for MCSP, there's some sense, I don't want to get into it too much, in which it like requires new circuit lower bound techniques, and it gives you like a problem to attack that's like kind of intermediate between like proving new, more powerful lower bounds and stuff that we can actually do. And so that might have sounded a little vague. So let me give you an example. So recently I had some MCSP hardness results. It doesn't really matter what it is, but what was cool is that as a result of trying to prove that NP's hardness result, it forced me to get a new circuit lower bound. And that circuit lower bound is kind of very different from a lot of the existing circuit lower bounds that we know. And so, this part, the exact circuit lower bound that I'm going to mention to you is going to be kind of technical. If you don't know what I'm saying here, don't worry about it. But it says that there exists a function, and actually this proof is existential, it's not explicit. It says there exists some function that requires 2 to the omega sub d of n more wires to compute with a depth d formula versus a depth d plus 1 formula. So you can talk about this model, whatever it is, of depth d formulas and depth d plus 1 formulas, and you can ask, for a function, how much can this depth decrease when I give you an extra layer of depth? How much easier can that function get? And in particular, I'm concerned with it additively. And like so we have a lot of good tools for analyzing constant depth formulas, but they all get stuck in like a regime of like 2 to the n to the 1 over d. And actually here you get like an exponentially better dependence on d, which is kind of cool. I mean, the proof is like non-explicit, like, but actually even before this result, it wasn't clear, like a random function doesn't give you this. So it wasn't clear whether any function should exist that has this property. And as like a result of like proving some hardness result for the constant depth formula version of MCSP, you got like this new circuit lower bound. So this is just like, I'm just trying to give you an example of like how thinking about MCSP can force you to prove like different looking circuit lower bounds, and that can lead you to some interesting things.
Why did you say wires with the formula?
Oh, I just didn't want to define leaves.
Okay.
Yeah, in case somebody is not familiar with formulas. Yeah, does that make sense? And this notation just means some constant depending on d. Okay. And so the second thing that I think is interesting, reason why it's interesting to prove hardness is cryptography. And I've kind of already hinted at this previously. So we know that hardness of MCSP is necessary for the existence of cryptography. If the problem was in P, then one-way functions can't exist. And what that means is if you're someone who's interested in the foundations of cryptography and you'd like to put one-way functions on like maybe a more solid complexity theoretic ground, you're going to need some assumption that also proves the hardness of MCSP.
You mean NP hardness or just mean hard?
Oh, any hardness, let's just say. Yeah, that's a good question. Yeah, I guess maybe I should just say intractability of MCSP. That would be better. So intractability of MCSP is necessary for the existence of cryptography. So if you would like to come up with some like foundations of cryptography assumption that would imply one-way functions, whatever assumption you use also needs to imply the intractability of MCSP. So I think because of that, it's interesting to study, what assumptions can we use that do imply the intractability of MCSP. And this line of research gets even more interesting with like recent work because seems possible that intractability of MCSP is actually equivalent to the existence of cryptography. So I mentioned this line of work earlier, like giving a worst case to average case reduction for some version of MCSP, and also showing that like the average case version of MCSP is equivalent to cryptography. If you could combine those two things, then you get that the existence of cryptography is equivalent to the intractability of MCSP. And then it would be really interesting to understand, is MCSP NPR? What assumptions can we show under which can we show MCSP is intractable? Did that make sense? Okay, great. And then the last thing is just like curiosity. This problem has vexed me a lot. I want to know, like, it's a simple problem, like about circuits, and like it's been asked since like the 1950s. Like, I want to know, is it hard? Is it NP intermediate? Maybe even being NP intermediate would be more interesting. But yeah, so this is the last of my like background and motivation slides. So if you have any questions about the problem, or like even like general questions about it, like yeah, feel free to ask. Great. So now let me just review what we've said so far. Define the minimum formula size problem. We said what makes it interesting is kind of the mystery that surrounds it and the connections it has. I think fundamentally the reason why it's hard to prove hardness is that we don't know good circuit or formula lower bounds. So that seems to be the fundamental reason. I'll kind of change, I'll like make an addendum on this later, but yeah. Okay, so now let me talk about our results. So this is the IS. So I thought this, I made this joke earlier, and I thought it was appropriate to include. So Einstein worked on a slightly different version of MCSP. So let me state the main results informally, and then I'm going to state them formally. So what I'm going to do here is I'm going to give you an informal statement of the theorems, and then I'm going to give you a formal definition of the minimum formula size problem, and I'll tell you about remind you a little bit about formulas in case you forgot. And yeah, so okay, so there's going to be two main results here. So just as a reminder, MFSP stands for the minimum formula size problem, and the first result is going to say that if the exponential time hypothesis, which was just the strengthening of P versus NP, holds, then the minimum formula size problem is not repeated. And the second thing is going to be MFSP has a search decision reduction, and this runs in polynomial time. And so search decision reduction basically says if you can solve the decision problem, you can solve the search problem. So in this case, you can print an optimal formula for a truth table given a decision oracle for deciding the decision problem. This will be more clear when I give the formal statement of this. It also might not be clear why this is so interesting. I'll tell you why. Okay. So those are the informal statements of the results. So now let me just give you a formal definition of the minimum formula size problem. Maybe it's clear completely to you now, but I'll just review this. So the model of formulas, you're given this like graph, which is like a rooted tree. For us, we're going to be concerned with De Morgan formulas. So it's going to be internal nodes are going to be labeled by and, leaves, and or sorry, and gates and or gates, fan in 2. Each one of these like gates only has fan out 1, and the leaves are labeled by variables or their negations. So like this leaf of the tree is like x5, and so the way you evaluate this thing is you kind of work up from the leaves. You look at whatever variable this is, you plug it into this or and go up the thing. And for us, the size of the formula is going to be like the number of leaves in this tree, like so the number of things at the bottom. So does that make sense? Maybe everybody here knows this, and maybe. Okay, cool. And then recall our definition of the minimum formula size problem is, you're given this like really long description of your input function. You're given some size threshold, maybe it's a unary, it actually doesn't really matter. And then the output is going to be, is there at most S leaves computing F? Before I defined it in terms of gates or wires, but yeah. And for formulas, traditionally you define in terms of leaves. Any questions about the definition of the problem or the model? Great. Okay, so now I can tell you what the main theorem is. So our main theorem is that this problem is not, well, you probably guessed it by this point. The minimum formula size problem is not in P under ETH. Yeah.
So maybe it's worth saying what the relationship between the complexity of the minimum formula size and the minimum circuit size problems is.
Yeah, great question. So formulas as a model are weaker than circuits. So anything, if you can compute something with any formula of size S is also a circuit of size S. So formulas as a model is weaker than circuits. And so you might think, because formulas are weaker than circuits, there's a reduction from the minimum formula size problem to the minimum circuit size problem. But this is not true. As far as we know, if you take two different classes, such that one contains the other, and you look at the various, or sorry, two different like circuit models and one that generalizes the other, we don't know how to relate the minimum circuit size problem on these two things. And this is kind of something that's strange. I mean, it seems obvious to us that like, you know, if the minimum formula size problem is not in P under ETH, then the minimum circuit size problem should not be P under ETH. Because like, if it's hard to do it for formulas, you know, circuits are only more complicated. It should be hard for that. Unfortunately, we don't know how to make that intuition formal. And somehow it seems related to the fact that like, I don't know, like giving a reduction that shows hardness for MCSP is somehow crucially talking about, is making use of lower bounds for that model. And if you go to a stronger model, maybe now these lower bounds don't hold or something like that. Does that make sense to everyone? Yeah, that's a great question. I should have pointed that out. So, you know, the conjecture that I presented earlier is that the minimum circuit size problem is not in P under ETH. That's still wide open. And my contention is, I don't think you need like super powerful stuff to get that. I think you just need like one new idea to build on gate elimination, like really simple lower bounds that we've known for like 40 years on circuits. And then you could probably maybe show that problem is not in P under ETH. I don't know how to do it, but yeah, good question. And so let me just tell you some notes about this theorem. So the first thing is that this holds in the case of like a De Morgan formula. So and this is the usual model of formulas. Actually, it should also work in like their favorite basis. Like so, for example, like the B2 basis, although the case analysis will increase. So if you know what that is, then great. If you don't know, whatever, it doesn't matter. Another thing is you can ask like, okay, how not in P do we show this problem is? And it's like just barely not in P. So I can show that if this is like not in time n to the log n, which is just ridiculous as far like this is, I mean, this is so close to polynomial, but it's not. So the lower bound is in time n to the log n. Remember, this capital N here is like the length of the input, right? And another thing is that it actually holds on the size parameter. So the size parameter S can be quite small. So it's allowed to be like poly n, and n is logarithmic in capital N. And the last thing is, if you're interested, this is like a deterministic sub-exponential time two-query reduction. But okay, those are the notes about the main theorem. So later in the talk, depending on how much time we have, I'm going to tell you a little bit about how it's improved. But this is the statement of the results. Is there any questions about the statement? Or okay, great. And the other result that I want to, okay, and that in our talk outline answers the fourth question, which is, what is our main result? This problem is not in P under ETH. And so another result here that we are able to prove is a search decision reduction. It might not be clear why this is interesting. So let me mention why it's interesting. So it's been an open question for about 20 years as to whether the minimum circuit size problem has a search decision reduction. And so what's a search decision reduction? It says that if you can solve the decision problem, then you can solve the search problem. So for SAT, it says like, if you can check whether a formula is satisfiable, then it says you can actually find a satisfying assignment. And for SAT, it's very simple. You know, you start by plugging in a variable, you check if it's satisfiable. If so, then you set it to that variable and you keep going. So because SAT is NP complete, it actually means that any NP complete problem needs to have a search decision reduction. So you could ask, MCSP is a problem, we don't know whether it's NP complete. You might, maybe you think it's not NP complete. Then you might be like, okay, does this even have the properties we expect of NP complete problems? And an NP complete problem needs to have a search decision reduction. So like, does it have a search decision reduction? You can ask that question. And a problem that like has that I've thought about a lot is it's still completely open that to rule out the possibility that the decision version of MCSP, there's an algorithm that runs in linear time, and the search problem requires like brute force. Like we can't rule out this possibility that the decision problem is like very fast, very easy to solve, but the search problem requires exponential time. So that, yeah, I think it should be possible to like, rule out a linear time, rule out this like linear decision exponential search possibility, but it's still open. Does that make sense? Was there any questions about that? Okay. And so then the theorem we prove is that this minimum formula size problem, you can actually get a polynomial time search decision reduction for it. And if in comparison to our previous result, this is kind of interesting because our previous result was saying using like sub-exponential time reductions, we can get an NP hardness proof. So you might expect if we got a search decision reduction here, it would be sub-exponential time, but actually we can do some like trickery and make this polynomial time reduction. So I won't talk too much about how this result is proved. You'll see some of the elements of it. But I do want to mention that this is, if you know anything about like this relativization barrier or something like that, it's interesting because this search decision reduction does not relativize. So in some sense, and it kind of makes sense because the reduction is using properties of formulas. It's like using the basis and stuff like that. And so it does not relativize. So that's pretty cool. Okay, so those are the statements of my two results. Are there any questions about the statements or even like general high level questions about MCSP and what might be interesting? Okay, great. So that sets us up for some techniques. So I'll tell you a little bit about how the stuff is proved. How much time do I have?
Let's see. Probably a little under half an hour.
Oh, okay, great.
I think it's 12:30.
Oh, no, it's 12:15.
But we usually go over.
Oh, okay.
Maybe make it 20, 25 minutes.
Okay, yeah, I think I'll probably be able to finish up by 12:15. So I'll say a little bit about techniques. And so, the proof is kind of technical, so I'm not going to give you any like formal proofs or anything. I guess maybe there'll be like one line proof or something like that. But I do want to give you like the high level way that this is proved. And so I want to tell you about like the road to ETH hardness from FSP. And there's kind of like 3 steps along this road. So the first one, it's probably not even going to be clear what these things mean, but for now you can just, there's going to be 3 steps along this road, and I'm going to describe them one by one. So the first step is focusing on small size thresholds. So this is actually related to like this stuff over here about like how hard you need your no instances to be and switching from polynomial time reductions to sub-exponential time reductions. So the first step in this proof is to focus in on small size thresholds. So size threshold is just this S parameter that comes around with MCSP, like what value of S you care about having the lower bound against. And the reason to concentrate on small size thresholds, so kind of the intuition is, proving like a polynomial time NP hardness result for MCSP/MFSP seems difficult. And the intuition I gave you for this was that it is because it requires strong lower bounds. So then you can ask, okay, well, what could we hope to prove with weak lower bounds? Like maybe, we can't prove NP hardness, but we could prove something weaker. Like what's the best we could hope to prove using lower bounds we already have? And as I kind of mentioned over here, the best algorithm for solving minimum formula size problem runs in time roughly n to the s. And this is just the brute force algorithm. Oh, okay, and here's the reminder that like capital N equal to 2 to the n is the length of the input, and little n is like the number of inputs to the function. And this is just the brute force algorithm. So in particular, the number of n variable formulas of size s is roughly n to the s. And the way you can see this, okay, it's not totally clear that this should be the dominating term, but if you had a formula of size s and it had s leaves, then you could imagine like swapping out all of the, you have n variable choices for each one of the leaves in here. So that'll give you like an n to the s lower bound. And it turns out that that's the dominating effect. Does that make sense? So there's roughly n to the s formulas. And actually this like, and if you can also write n to the s as like 2 to the s log n, and this extra log n over here is really going to be our c when we get to our proof. So our best algorithm for MFSP runs in time n to the s. And why is that interesting? What's interesting about that is that that's already super polynomial time, even when the size parameter is n. So n here is the number of inputs to the function f. So even in the case where your size parameter is like basically as small as it can be for a function that depends on all of its inputs, already this algorithm runs in super polynomial time. So what you could hope for, and so here's the calculation that shows this in super polynomial time. So you have like 2 to the s log n. If s is equal to little n, then 2 to the s is going to be equal to capital N, and then log little n becomes log capital N. And so what that means is if this brute force algorithm is optimal, you could hope to show the minimum formula sizes in P just by considering small size things. And we know cubic lower bounds for formulas, and we know linear lower bounds for circuits. So what's stopping us? Like if this brute force algorithm is probably optimal. I mean, if it isn't optimal, then it would say that like there are limits to how good of crypto you could get. Because algorithms for MCSP or MFSP can be used to defeat crypto. So like non-trivial algorithms for this problem would show that like you couldn't get like really strong cryptographic things. If that didn't make sense, don't worry about it. But anyway, if brute force is optimal, you could hope to show lower bounds in the small size regime. We already know, we have linear bounds even for circuits. So like, why can't you use those linear lower bounds in order to show hardness for MCSP? Like, and cubic lower bounds for formulas. So like, what's stopping us? And so like, this is the part that like really bugs me. It's like, we have lower bounds for linear lower bounds for circuits. Those should be good enough to prove hardness for MCSP. I don't know. And if you're interested, I can tell you a little bit about like in what sense these linear lower bounds aren't quite good enough to give us circuits, a hardness for MCSP, but it's not like a quantitative thing. It's like we don't need even harder functions. We just need different looking linear circuit lower bounds. These linear circuit lower bounds that we already have there, in some sense, they're like too recognizable or something like that. Like they apply really to like, I don't want to get into it too much, but yeah.
So would such a result be interesting? And wouldn't the minimum circuit size problem don't we think of it as interesting only when you put a range that's kind of hard for the function? So maybe it's not in P for linear size circuits, but it's in P for kind of deciding if it's
I see.
cubic or sub-exponential.
I see. So you actually can do like some sort of padding argument to say like if it's not in P for the small size threshold regime, then it can't be in P for any size threshold regime greater than linear. Does that make sense? So basically what you can do is you can just add in some extra inputs that the function never looks at. And then like, oh wait, am I doing this in the wrong direction? Yeah, sorry, I'm doing it in the wrong direction. Yeah.
You can prove something like this, let's say for tensor rank. We know it's NP hard to compute tensor rank, but the proof uses the easy regime like n and n+1.
I see.
I don't know much about anything else than that.
I see. Yeah, so that is a possibility, I suppose. That like you're saying maybe in this size regime, it's actually harder than in the hard regime. That's fair. I think this regime, it's unlikely that you'd have some sort of like non-monotonicity with respect to the S, because like because this like brute force algorithm really should be optimal. But yeah, that's a fair criticism. Like maybe that this size regime is not interesting. I don't know. I think it's interesting. Does that answer your question, or yeah? Okay. Right. And in this regime, like it's not even easy yet, like to show that MCSP is not in P. But it looks like you'll need one new idea or something like that. Okay. So this was like, what is our approach? The first step in our approach is focusing on the small threshold regime, because that's the regime where we have lower bounds. And can we make these lower bounds good enough to show that the minimum formula size problem or the minimum circuit size problem is not in P? And so then the second idea on the road to ETH hardness is to focus on the partial function version of the problem. So what do? We focus in on this like intermediate problem for MFSP, which I'm going to define for you now. You can probably guess what this is going to be, but your input is going to be the truth table of a partial function f. So now this function maps from 0, 1 to the n to 0, 1 star. So you'll have to output star. And I still want to stress that this is still like a really long input. Like we're not using some succinct representation of this to cheat or anything like that. Like you have to, still write down a 2 to the n length string here, even if most of it's stars. And then you get some size threshold s, and you output, does there exist a formula of size at most s computing f, where now you don't care about what the values on the stars are. Does that make sense? So yeah, it's basically computing partial functions with a formula. And it turned out, oh, and I want to emphasize actually this idea of looking at the partial function version first is like not, it's something that's been used before. So like we know that the DNF versions of MFSP are hard, and they also worked by focusing in on the partial function version first. Actually, I think Tony is in this paper. And so I was able to prove this, I guess like 1.5 years ago or something. I was able to show that this problem is hard if you look at the partial function version. And in fact, it's hard even for circuits. And so you can show that like under ETH, there is no end to the little log law. Basically, this problem's not in P. So the step 2 of the thing is showing that this partial function version is not in P. And so that's the result we use in step 2. On the next slide, I'm going to give you some intuition for how this is proved. But are there any questions about the statement?
Just occurred to me that last week we heard a talk about partial learning consequences.
Oh, really?
Totally different argument. Similar.
Oh, that's funny. Okay, so let me tell you a little bit about how this is proved. This lower bound actually even holds in this regime where s is equal to n, so it's like linear in the number of inputs. And this is kind of interesting actually, because this is like a very strong result in the sense that like, what I'm saying is, if you like look at how this theorem is proved, it's actually saying if I give you a partial truth table, even recognizing whether it's computable by read once formula. If you know what a read once formula is, then great. If you don't know, then don't worry about it. But a read once formula is probably the weakest model computation that you could possibly imagine. And at least for partial functions, it's actually hard to tell whether it's computable by a read once formula. And that's in strong contrast to the total function case. In the total function case, it's very easy to check whether it's computable by read once formula. But for partial functions, you can actually like put the stars in like clever places and make it hard to tell. Anyway, that's just an aside if you like read once formulas. All right, so how is this proved? It actually has like a nice kernel of an idea. I mean, it's kind of complicated, so I'll just try and give you this kernel of the idea. And the kernel of the idea is actually this OR function, very simple function that we have like a trivial lower bound against, has a very nice property. And that property is that it has a lot of optimal formulas. So if you're computing the OR function, you can compute OR in like whichever way you like x, you could OR x1 to xn, or you could permute those variables and then OR them together. So as a result, there are like n factorial optimal formulas for this. So that's a lot. And n factorial, maybe this hints towards my lower bound, is like n to the capital N to the log n, which is like basically the lower bound we get. And this is also like roughly equal to the number of formulas of size n, whatever. But anyway, the kernel is that this OR function has this interesting property, or like basically any symmetric function that has a lot of optimal formulas. So then that raises the following question. Could you somehow construct some function where in order to compute that function, you might have to choose one of these n factorial many optimal circuits for OR. Like maybe there's some big function, and in that big function, you need to compute an OR. And some of these ORs are actually more efficient than other ones of these ORs. And so you need to pick one of them. And maybe that choice of which OR circuit you use corresponds to a permutation. Maybe. It is something you hope to do. Does that make sense? Okay. And it turns out that this is possible. I won't tell you so much about how it's possible, but there's this problem that sounds kind of nasty, but it's actually quite nice. 2n by 2n bipartite permutation independent set. It's like taking every NP-complete problem and putting all their names together. And it was shown earlier by people interested in parametric complexity that this requires like 2 to the n log n time under ETH. And we're actually able to give a reduction from this problem to computing the complexity of partial functions. And so I won't tell you too much about how that's proved. I mean, so what you get is that if you get a yes instance of bipartite permutation is independent set if only if this formula has this partial function has a formula of size 3n. If you're interested in what that formula looks like, it's actually like not so crazy. It's like saying like this is some permutation problem, and like the formula you get that will compute this partial function is going to involve some permutation down here, and like this is like the hidden OR that we're talking about here, but yeah, okay. And like this, the thrust of the proof here is like somehow based on gate elimination with like some twists on it. Okay, are there any questions about this?
What's the problem?
2n by 2n,
Yeah.
yeah. It's it says you're given a what's the best way to say this? So your output is going to be some permutation on, I think it's 2n. So that's your output, and it's going to be subject to constraints, or I guess this is going to be does there exist a permutation pi? And this subject to constraints, and those constraints are going to be basically of the form if pi of I is equal to j, then pi of k is not equal to I don't know, w. So there's going to be some bipartite graph. I mean, you could phrase this is like an equivalent way to phrase it. You basically get implications of the following form. If the permutation maps one thing to something else, then it can't map the permutation over here to something else. And there's a couple other constraints like permutation pi of n must be n, it must fix n, and then like pi of n plus 1 to 2n. It's supposed to be mapped to. I guess I can call that set. Maybe like n. But it's going to be some version of. Does this make sense? Or are you able to see this also? So you're going to be given constraints of the following form, like if the permutation maps I to j, then it can't map k to w. And you're also going to have to satisfy some like that the numbers 1 up to n are all mapped to the numbers 1 up to n, and the numbers n plus 1 up to 2n are mapped to the n plus 1 up to 2n. And then the question is, does such a permutation exist? There might be one other condition, but I think these are the main conditions. And so this is, you can think of it as like, this is some permutation problem that under ETH, you can show it requires basically 2 to the, because 2 to the n log n is like n factorial time. And so like, yeah, the natural thing to do here is like brute force algorithm in factorial time. And so if you want to know this, there's this, the smart way to come up with this result would have been, hey, this is the OR function. This looks kind of like a permutation. Let me find a permutation problem that's hard. Let me try and map MFSP to a permutation problem that's hard. Like that would be the smart way to come up with instruction. That's not what I did. I like worked backwards, and then I went into like Ryan Williams is my advisor. I like went into his office. I was like, hey, I have these problems. I have these like instances which I think are hard for MFSP. Like I'm interested in like problems which require time roughly this in ETH. And like he gave me like a bunch of papers. He gave me like 7 papers that like in fine grained complexity used like this stuff. And actually it turned out that none of the results in this paper were able to give me that. And then somehow, for some reason, I stumbled upon this paper, which I was looking in fine grained complexity when I guess I should have been looking at, this was more in the parameterized complexity to the whatever extent that they're different realm. And so then I stumbled upon this problem, and then with some work, we were able to get this to happen. But yeah, it was kind of a work backwards kind of thing. Anyway, any other questions? All right, great. So that was step 2, show hardness for partial functions. And that just leaves the last thing that I want to say, which is whatever step 3 is in this approach. So what's our time here? Oh, I see. Yeah, sorry. I didn't even notice the clock. Okay, so I'll try and finish up fast. So the last step is to reduce the partial function version to the total function version. And the way that we do it is we actually give a fine grained reduction from the partial function to the total function version. the result in step 2 is that the partial function version is hard under ETH. And what we do is we actually give a reduction between the total function version and the partial function version. That reduction actually runs in exponential time. It's like time 2 to the order s plus n. But it's better than brute force. And that's why I call this like a fine-grained reduction. So when the size parameter is very small, this actually runs in polynomial time. And then if you combine these two things, you'll get that the minimal formula size problem is not in P under ETH. So we knew that the partial function version is hard. What you'd like to do is reduce the partial function version to the total function version, which I tried to do for some time. But that doesn't really work. But it turns out, I mean, you don't need to give a polynomial time reduction between the two things. You can get away with an exponential time reduction as long as it plays nicely with the size parameter s. And it turns out you actually can do that. Great. And then you combine these two results and you get this. In order to prove this, there's kind of some main lemma. But since I'm over time, maybe if you're interested, I can tell you in very. Oh, what?
Maybe after lunch if you have time.
Yeah. But great. And so let me just summarize the talk for you. These are kind of the 5 takeaways. What is the minimum formula size problem? Compute the formula complexity of a given function. What makes this problem interesting? I think it's the connections it has and the mystery surrounding it. Why is it hard to prove hardness? Well, on the one hand, it's because seems to be because we don't know good circular formula lower bounds. But on the other hand, even in regimes like the linear size regime where we already know circuit lower bounds, it still seems hard to prove hardness for the problem. So what's going on there? Is there some barrier that we don't understand? Or is there just some technique that you can use to show hardness? And our main result is to show this problem is formula size problem is not in P under ETH. And we do it by focusing on the small threshold case, and then doing this 2-step reduction, which goes through the partial function version in the intermediate step. And so, great. Thank you so much for listening to the talk. I'm sorry for keeping you over for a few minutes. So there are some interesting open questions. There's so many open questions related to MCSP. There's all these things, connections, which I didn't really talk about too much, but if you want me to talk about them, I can talk about them. And so if you can extend these connections, that would be great. If you could find something else that it's connected to, that would also be great. In terms of hardness, there's this problem that I've been harping on. Can you show that MCSP is not in P under ETH? Yeah, it should be possible. Yeah, I think you just need one new idea or something like that. But also there's related to the minimum formula size problems. Can you prove some hardness for approximation? Or can you prove something better than this n to the log n? If you use cubic lower bounds for formulas, you should be able to do something better than n to the log n. You should be able to get a cube in the exponent. I don't know how to do it. Because if you think about it, it's very weird that in order to prove hardness for formulas, I'm really only using this or lower bound, which is very simple. We know much more powerful lower bounds for formulas. Why can't we use them to get better hardness? I don't know. Anyway, thank you so much for listening to my talk. Yeah, if you have any questions, I'd be happy to answer.
Thank
you. Maybe this doesn't make much sense, but is this problem much simpler if things are algebraic? If I just tell you that I give you a set of monomials, so what's the smallest algebraic circuit itself?
Yeah, that's a good question. So I think the other Rahul Santanan has studied this question. I'm not totally sure. I'm pretty sure there's no better algorithm for it than brute force. I don't know if it's also has this similar thing where it has connections to other areas or stuff, and I don't think there's hardness for it either. But I'm not totally sure. It's not my area, but I think it is interesting to study an algebraic version of this question.
So the connections you mentioned, things say if MCSP is NP complete, then X is not equal to ZPP and things like this. So in what parameter regime of MCSP do these connections hold?
That connection holds for any parameter regime. The thing is, it seems in order to prove NP hardness, you're going to need to use the large regime case, just because otherwise you give an algorithm for SAT. But that result that says if you have NP hardness, then you get this. It doesn't depend on what you're doing with the size parameter. You can actually use any size parameter for that. So if for whatever reason you're able to show that this problem is NP hard even when the size parameter is small, that would still prove X is not equal to ZPP. Although it would probably put P quasi-polynomial time equal to NP. So yeah. Yeah, does that answer your question? Okay, great. Yeah.
Two quick, hopefully real quick questions. One is, do you know about the partial version of MCSP? Do you know?
Yeah, that the same result that shows that the partial version of MFSP is not in P under ETH also shows that the partial version of MCSP is not in P under ETH. So yeah, it's very, very tantalizing to show that MCSP is not in P under ETH by giving a reduction between the partial function version and the total function version. And yeah, I was actually the story of this MFSP result is kind of interesting because I was very skeptical that you could do this for formulas or circuits. I think even when I wrote the paper, I was like, I mean, you could hope to give a reduction between the partial and the total thing. I was like, I was like, I don't know if that's so viable. Maybe I think there's a more direct approach, and I pointed out something else. And then it turned out I was completely wrong. And for formulas, you could give a reduction from the partial thing to the total thing. So, is there a reduction from the total partial thing to the total thing for circuits? I don't know. Like I thought about it and like I don't know how to do it. Somehow, I mean, formulas are very nice. Like I didn't get to say it, but kind of in this main lemma that we use, there's this like leaf weighting technique proved by Buchführer and Umans. And this leaf weighting technique is like the kind of the key reason for us to be able to like connect the formula complexity of partial functions to the formula complexity of total functions. And there really doesn't seem to be an analog of this in the circuit world, but maybe there's something else you could do.
But for monotone circuits or formulas, there must be a version of this. Is it easy?
No one knows if it's odd or not. Actually, there is. I think if, in fact, so it's. I think that problem is actually one of the exception to this rule. I told you that there's not really reductions between different versions of MCSP for different circuit classes, but I believe. The other Rahul told me, but I've never seen it written down. There is actually a reduction from MCSP to like monotone MCSP. So this problem should only be harder.
Lower bound, strong lower bounds for the class to get hardness.
Well, I mean, even if you get hardness for this, it doesn't imply hardness for this, right? Is that, or am I misunderstanding your question?
Maybe I'm misunderstanding what you're saying.
Oh, I'm saying.
I think Tony is saying that there's that barrier you were talking about wouldn't hold for monotone MC.
Yeah,
because we do have lower bounds.
No, we do have lower bounds for that. But I guess getting hard, so this problem is only harder than MCSP. So if we prove that this problem is NP hard, it doesn't necessarily imply that MCSP is NP hard. Or maybe
Right, but do we know it about monotone?
Oh, okay. Yeah, we don't know it. Yeah. So even though we have strong lower bounds against this class, again, we're running into this problem that like, it seems like the lower bounds you need to prove hardness for MCSP are like a different flavor than the usual lower bounds that we have. So yeah, I think this is a tantalizing question. Like, can you show that this problem is NP hard? I see what you're asking. Yeah, and yeah, you're right. That does go against this intuition that the only thing stopping us is that we don't have good circuit lower bounds. It's somehow like we need circuit lower bounds of the right flavor or something like that. And that getting circuit bounds of the right flavor, I think, is this like nice intermediate question, because you can ask them, do we have circuit bounds of the right flavor, even for like linear size regime? And we know how to prove linear size lower bounds already. So here's an intermediate question: like, can you get lower bounds of the right flavor in order to rule that MCSP is not in P? A linear regime or something like that.
Okay, let's go lunch. Thank you.